The alternating series test will give us a simple way to tell when we have an alternating series when it converges. At least it will give us a sufficient condition for the series to converge. The alternating series test tells you if you start with an alternating series, so it has to be of this standard form for alternating series. Remember, to be an alternating series, we need this b sub n to be positive for all n, and then the signs alternate because of that term minus 1 to the n minus 1. If you're so lucky that the sequence of the b sub n's, that's not the sequence of this entire term, but just the b sub n's, so these positive numbers, if that sequence is decreasing and has limit 0, then the alternating series test tells you the sequence really must converge, definitely. And the first thing I'll point out is, this doesn't tell us how fast the terms have to go to 0. They could go to 0 very slowly. It doesn't matter. As long as they tend to 0, and it's a decreasing sequence, you can't have them getting bigger and smaller and bigger and smaller. They have to be decreasing and tending to 0. Then we can be sure the alternating series will converge. And I'll show you why that is. Let's look at these partial sums one more time. The first partial sum, of course, is b1. The second partial sum is b1 minus b2. As we've said before, that gets smaller. So you start with b1, some positive number, then it gets smaller. The third partial sum is b1 minus b2 plus b3. So you get bigger again. Notice, though, that even though S3 is bigger than S2, you don't get all the way back up to S1, because minus B2 plus B3 is still negative, because the B's are decreasing. The B2 in magnitude is bigger than B3. So S3 is smaller than S1, but it's certainly bigger than S2. S4 is B1 minus B2 plus B3 minus B4. Notice that this, of course, gets smaller than the previous one, S3, but it's still bigger than S2, because this B3 minus B4, which is what you have to add from S to S2 to get S4, is certainly positive because the B's are decreasing. B4 is smaller than B3. And we can continue on like this. If we graph the sequence S sub n, and remember what it means to graph the sequence. We're going to be putting n along this horizontal axis. 1, 2, 3, 4, 5, 6. And here we're going to put s sub n along what's normally the y-axis. We're going to start up here at b1. That height will be b1. That's s sub 1. Then S2 is B1 minus B2. Now that could be positive or negative, it doesn't matter. I'll just draw it as if it's still positive, but it's definitely smaller than B1. So this, I'm just going to write here is B1 minus B2. That's S2. I won't put all of them here. S3, you go back up higher. You're still less than S1. S4, you get smaller than S3, but you stay bigger than S2. S5, you get bigger than S4, but still smaller than S3. So the partial sums alternate getting bigger and smaller, where these are all the odd index partial sums. The ones up here, and the others, I won't write this in, are the even index partial sums. You notice these odd index partial sums are getting smaller and smaller as you get bigger odd numbers for the index. The even index partial sums are getting bigger and bigger, and these will have to stay below these. The series converges to some number L if these partial sums all end up, let me put a dotted line here for L, if they all end up getting really close to this number L. And I claim that's guaranteed to happen if the sequence B sub n is decreasing and the limit of B sub n is 0. Why is that? Well, we've already seen if the B's are decreasing, then the partial sums have this pattern. The fact that the B sub n's have limit 0 is important to us because the difference between, for example, S5 and S6 is exactly B sub 5. Let me write that in here. S5 is B1 minus B2 plus B3 minus B4 plus B5. That's a 5. And then S6 is b1 minus b2 plus b3 minus b4 plus b5. Oops, I apologize for that again. This is plus b5 minus b6. So notice that to get from s5 to s6, to get from the vertical coordinate here to here, that this difference here is exactly b6. When I go to the next one, the difference here will be b7, etc. If the b's get closer and closer to 0, then these get tighter and tighter together, and we'll get closer and closer to this number L in the middle. Eventually, they'll settle in and get arbitrarily close to L. So what's our conclusion? The series definitely converges if you have an alternating series with these two simple conditions holding. So you just have to always check those two conditions when you have an alternating series. If they hold, you know the series converges. Now let's talk about the alternating series test error estimate. Once we have an alternating series, one for which the alternating series test applies, and we know it converges, how can we approximate it? Well, just as always, we want to use the partial sums S sub n to approximate the full series S. So remember here, S will be the sum of minus 1 to the n minus 1 b sub n, here n equals 1 to infinity, and the partial sum S sub n will just be b1 minus b2 plus b3 minus b4, and then we'll keep going like this, plus, and I'll write plus or minus b sub n. It'll be a plus if n is odd, it'll be a minus if n is even. But we have exactly n terms here, ending with plus or minus b sub n, as I said, depending on the parity of n. And then we ask, what is Rn? Not really what is Rn, how big is R sub n? First of all, what is R sub n? R sub n is just S minus S sub n, the difference between the actual sum and this partial sum. And to help us understand the answer, we just have to look back at the previous picture. So I'm going to flip back here. You'll see that when you have a series that satisfies the alternating series test hypotheses, this number L, which is actually the same thing that I've been calling capital S, so I'll call it S instead, the even partial sums stay below S, the odd partial sums stay above S. But just a single term, whether you subtract it from an odd partial sum or you're adding a positive number to the even partial sum, a single term jumps you across the actual value of the series S. What does that mean here? It means that the size of R sub n, what I said here, must be, that's the difference between the actual sum and S sub n, must be smaller than the next individual term, which is b sub n plus 1. Now, notice here that R sub n will be positive here if n is even. Because remember from the previous picture, the even partial sums were smaller than the actual sum, and R sub n will be negative if n is odd. But if we don't care about in which direction we're wrong when we use S sub n to approximate S, and you only care about how much we're wrong, this tells you the size of our error is less than the size of the next term. And of course you can tell in which direction we're wrong as well using this. The error is positive if n is even, and the error is negative if n is odd. But you have to interpret this correctly. Remember, saying the error is positive if n is even means the even partial sums are underestimates, and the odd partial sums here are overestimates.